But to me, we watched a video on, related to this chapter, one of those authors' videos, a waypoint video in, oh, wait a minute. Anybody do a sundial thing? I forgot. I'm still gonna.
I'm sorry.
Don't forget, let me know if you have any questions, but you can get lab credit using doing the sundial. And
That's due tomorrow.
what's that?
That would be due tomorrow, right?
No, wait. The first lab isn't due until, it's a while. I think I do, you can read my syllabus. You need to do 4 labs, and the first 2 labs are due like right around midterm, like October-ish, middle October, first 2 labs. But tomorrow at 8 o'clock, no, 8 o'clock, yeah, tomorrow at 8 p.m. Anybody plan to come to do that tomorrow? Yay, it'll be fun. Okay. So we'll be, any questions about where we'll be? Okay, so we have the normal parking lot, and then we have like a bigger parking lot, closer to like Hawthorne. Okay? Yeah. And so in that vein, if you go past the big parking lot, there's a hill there, and that's where I'll be set up. So look for the red light. So I think I have a lamp that shoots red light, which is better for our eyes to adjust to the darkness. So, yeah.
Does that one count as your own, or does it?
Yeah, oh yeah. So what I'm trying to say is you need to do 4 things, and yeah, that would count as one if you're on your own lab. Yes. Yeah. And if you did sundial, that would also count. And if you took a sky map and lined up the stars and found some constellations, that would count. So that's 3.
What was that app called?
What was that app
Do you
called?
remember going? It was Sky.
Stellarium?
Stellarium, that's on your computer.
That's the computer.
Sky.
Skyline?
What's that?
I said Skyline.
Walker.
It's like Sky.
I'll get it for next time.
Is that that thing where you?
Sky Safari. Yeah, it is Sky Safari. Yeah.
Cool. Okay.
Yeah, Sky Safari.
Sky.
So, yeah.
Sky.
And then one of the things, it's a little game that I play with you guys handing in a report for doing anything is you need to have a photo of you doing it. So if you come tomorrow night, which I hope you do, you need to take a selfie of you there with the telescope or something. It's part of your report, okay? If you have an issue with that, let me know, because we can work something out. All right, so we're still kind of talking about how the universe is laid out, okay? And actually, we're gonna, not so surprising, find that early on they didn't quite get it right, but that's the nature of science, is we keep building on what we know, okay? So when it talks about classical philosophers, we saw a video with this where basically I'll put E for Earth, and according to the classical philosophers, and it makes sense, they would see the sun, this is my sun, they would see the sun rise in the east and set in the west. And it goes counterclockwise, so it goes like this. Okay, so it looks like the sun orbits the Earth. And then actually, you can go ahead and add the planets orbiting the Earth. This is called the Ptolemy model, T-O-L-E-M-Y. The P is silent. And he was kind of the last philosopher that had this idea. And we're going to see it in the slides here, we saw it in the video, that he actually, if this is, I'll put a J for Jupiter, what he said was that Jupiter will go counterclockwise. Is it counterclockwise? Yeah. We'll go counterclockwise, but it will make these little loop-de-loos like epicycles. It will go this way, and then it'll go like that, and it'll go like this, it'll go like that. Like have these epicycles every so often. That's what he said Jupiter would do. And we're going to talk about this. Actually, you do, if you're into astrology, you know that when a planet goes retrograde, basically the planet is going backwards against the background stars is what it usually goes. So that's a big astrology thing. That's the Ptolemy model. Well, historically then, we have another couple of names. So Ptolemy was the last one. By the way, this is what we call the geocentric model. Geocentric model. And at the time, it was the model of the universe because all they really knew was, us. But the heliocentric model actually kind of had a turning point with Copernicus. So there's my sun, and of course, I'm going to go ahead and not make the full orbits, but we have Mercury, we have Venus, we have Earth, we have Mars, and then Jupiter, Saturn, Uranus, and Neptune. And actually, one of the labs we're going to do is try to convince you that definitely, as I've drawn enough like that, those are not drawn to scale. The farther you get out, especially with the gas giants, they are way far apart from each other. It's amazing. But anyway, this is what we call the heliocentric model. Helio meaning sun, centric meaning center. Heliocentric model of our solar system. Okay, and names like Copernicus, Tycho Brahe, Kepler, and actually Galileo, okay, was also definitely in this camp. So this is the real deal, this not so much, right? Okay, so one of the things, even before the scientific method, we talked a little bit about the scientific method here, I think. I get my opinion.
Yeah.
I thought so too. Before the scientific method, we all have curiosity. It's kind of how we're built. Okay, so I'm going to show you some slides that kind of show early on, not necessarily one of these models, but cultures would look to the skies and use them to their benefit. What's this? Stonehenge, yeah. Anybody been? No? Me neither. Project. Yeah. I'm going to dim the lights a little bit. But there's all sorts of geometries that happen when the sun is at its the solstices and the equinoxes. So this kind of shows the coolness of Stonehenge. From what I know, I've heard about it, there are not the fact that these stones are not readily available for where they are. Is this in, I don't even know what continent this is on.
Southwest England.
Thank you. In England, the stones are kind of unique to that area. So and there's a little person standing there, so you got a little bit of scale there. Yeah, so it's amazing that they would line them up so that they matched with the Earth's orbit around the sun. Oh my God. If we open the window, would it pull down in here? Maybe. Depends on if it's warm. I'll try it.
You gotta careful.
Oh, there's a stick there. Yeah. Yeah.
Oh, yeah.
We set you up.
Make it look easy.
This is another one for an ancient culture that, again, with I've got some notes here. With noon on the summer solstice. At noon on the summer solstice, the light goes right in the center there. And so these Indians were understood how the sun's position in the sky changed as the Earth orbits the sun. This one, wow. Okay, this is a fragment I'm reading. This is a fragment of a mammoth tusk that is 27,000 years old. It's found in Ukraine, and scribes have marked these edges, and they've been interpreted as a record of 4 cycles of the lunar phases. So it's just pretty cool. You know, this slide just kind of talks about historically the Greek philosophers would have been more like the Ptolemy model. Okay. So one of the things that the cultures had to overcome was this idea that, now this isn't necessarily a religious thing, although it could be, was that anything that's above the earth is perfect. With perfection brings a few things. With perfection brings the shape of a circle or a sphere. And with perfection also brings it never changes. And there are no, what we say, blemishes. Nothing's different about it. Okay? So those are kind of the obstacles that this philosophy kind of segued into the scientific method of understanding things. Folks had to kind of take that all into account. So this is what they thought. This is more like the Ptolemy model, okay, where we have the Earth in the center. It's kind of cooling off a little bit. We have the Earth in the center, and the planets orbiting the Earth, and the Sun orbiting the Earth, and all the stars orbited the Earth. Okay. So on the video, and I want you guys to do this. How should we do this? I'll stand back here so I can see the perspective. There's this thing called parallax, and it kind of related to that. Did you guys know this? That our eyeballs, our set of eyeballs, one eye is dominant and one eye is recessive. Okay. So the way parallax works is you can see the person holding their thumb out. So hold your thumb out and extend your arm. Okay, both eyes. And now close one eye and close the other eye. Close one eye, close the other eye. What happens to your thumb? Mine moves, mine shifts, yeah, left and right. So literally, all that is, oh, and then if you open them both, you can see, to find your dominant eye, you open them both and see which one it's most like. Which one it, yeah. So you have them both open, you see where it is, and then you close one, close the other. And whichever one it's more like, with both eyes open, with one eye open, that's your dominant eye. To me, it's my right eye.
How does that work though? Is it just like a trick, like a mind trick or something?
Well, it's what that's trying to do is to kind of show you with your right eye open, it's kind of like you're over here looking at your thumb.
Right.
With your left eye open, it's like you're over here looking at your thumb.
You're like dominant eye, like I don't know.
Yeah, forget the dominant eye bet, but with just one eye, it's like you're over here looking versus over here looking.
Okay.
And the thing that parallax counts on is that your thumb is relatively close. Okay, we're going to do another parallax example. Let's see, how do I want to do this? Instead of your thumb, I'm going to go ahead and I'm going to hold this, pull the shiny part up. I'm going to hold up my thermos. Okay, now not your thumb, but close one eye and close the other eye and see if it changes its position relative to the back of the board. Does it?
Yeah.
Does it still?
Yeah.
I thought not as much.
Does it? No, not as much.
I'm like
Okay,
lining it up.
so now I'm going to do it right here. Now do it.
Yeah.
And then when I do it back here.
A little bit. Right?
Yeah, a little bit, but not as much. Exactly, a little bit, but not as much. And so this effective parallax, the farther away an object is from you, actually, if we were to go outside, and sometimes I've done this with students, but we go outside, and if I stand way far away, and you kind of do one eye and another eye, you're not going to see parallax. Okay? You can also see parallax if you literally, to keep both eyes open, but you literally move from side to side. Okay? But if an object's far away, then no parallax. If an object's relatively close, yes, parallax. So there was this event, and we're going to talk more about oh yes, this is a miscellaneous slide. Forget, I'm coming up to that. This one, hold that thought about parallax. This actually just shows how fancy I think folks were at the time. This was a little experiment done in about 200 BC, and what they did was, I don't know how they did this, but they had two people, they timed their clocks, and basically they had a shaft of light come right down this well. Then they had, so we knew that the sun was right overhead, and then they had a shaft of light at the same time, a person that was over here, this is the Earth, was over here on the Earth. And of course we know that there would be a little bit of an angle effect. So the difference between it being straight up or versus straight up was 7 degrees. Okay, 7 degrees. 7 degrees is about 1/50th of a 1/50th of 360 degrees. So what they did was take that distance and say this must be 1/50th of this. Kind of cool. They did a math thing. Okay, so back to, let's hold that thought with parallax. Where did my slide go with parallax? It must be coming up. Okay. Whose model does this look like? Your choices, I'm going to ask you to say which one. Your choices are going to be heliocentric model or geocentric model. How many people think this looks like a heliocentric model? Yeah. How many people think it looks like a geocentric model? I think it looks like a geocentric model. Yeah, this would be like Ptolemy's model. And I mentioned the loop-de-loos. I kind of showed you, I call them loop-de-loos, but this kind of showed you Jupiter doing them. That's what he's showing you here. One of the things about a good solid scientific reality or a good solid model or a good hypothesis that can be elevated to a theory is that the more complicated you have to make it to fit what you think it is, the less likely it is true. It's called the keep it simple, stupid model, the KISS. I think I might have mentioned that before. So this actually is just getting too crazy. But you can see actually, and I think on the next slide, you're going to see this. I talked about retrograde motion of the planets that astrology is really interested in. And this would be the retrograde motion. This is what we call direct motion of the planet against the background stars. Okay, now this motion I'm talking about happens over the course of weeks and months. This subtle motion against the background stars. It's kind of cool. Okay, and usually it goes this way, but sometimes it goes this way. And this is how Ptolemy fixed it. Okay. So here we see, I think this was Mars. Usually they pick on Mars. And you can see the direct motion and the retrograde motion. So this would be, well, I'll pick this one. This is direct, retrograde, direct. Again, subtle, okay? Each one of those dots might be, I don't know if they represent a month, okay? But it's a subtle movement, and you can see the pattern stars. There's Virgo there, there's Leo there, moving against the background stars. So Copernicus, I'm going to go ahead and put Copernicus up here. He would be the heliocentric model. Can't spell Copernicus. Got two P's? Okay, thanks. Copernicus. So he wasn't the first to go with the sun in the center of our solar system, but he kind of revived it. Okay, so he was not the first. Probably the previous slide kind of said this. Even with Ptolemy doing these little loop-de-loos to kind of describe why we have these retrograde motions of the planets, that still couldn't totally account for the specific motion that we saw the planets do as they go retrograde. Okay, so something needed to give. So I'm going to ask you, is this heliocentric or geocentric? How many people think this is heliocentric? Yep, me too. Yeah. Be a good test question, wouldn't it? Draw the heliocentric model. Now, this is drawn to kind of show you what we mean by why retrograde motion happens. In order for this to make sense, you're going to have to know that Mercury moves fastest. Wait, so if I go ahead and say 1, 2, 3, 4, 5, 6, 7, 8, 9, I make this a fast scale, excuse me. So fastest is 1 and slowest is 9. Okay, on the fast scale, we have it going this way. What I'm trying to say is that as you get farther from the sun, and it's a gravity thing, we're going to talk more about gravity, but they go slower and slower and slower. So we've got two planets up here. The blue planet, make it Earth. The red planet, make it Mars. Okay. Now sometimes students will tell me, well, yeah, Neptune goes so slow out here because it's got a humongous orbit that it needs to, as if it completes one orbit around the sun, it's got a bigger circle. It's really an ellipse, but and no, it literally moves more slowly. So here we go. At position A, we have Earth, Mars. And if we were to look at Mars, you can see kind of against those blue twinkling things, those are the background stars. So we would see Mars at position A. Now remember, Mars is moving more slowly in its orbit. So position B, Earth goes farther, Mars not so far. Now you can see that relative to the background stars, it's gone in the direct motion. Okay, it's not retrograde. A to B, that's direct motion. Okay, but now what's going to happen is, why did they do this? It looks like it's backwards. It's like, I don't know, like I think they have the orbits. I'll grab my pen. Do you see my problem with this slide? I didn't make this figure. What's my problem? What direction do the planets orbit the sun? Counterclockwise. So I just think, let's see if I can make this bigger. Just think we need to change those, silly people. So this actually needs to go like this. I'm feeling better about that. Did you see how I changed it? Okay, A to B to C to D, these are positions. Okay, so A to B to C to D to E to F. Now, Earth is going faster in its orbit, so we say the Earth is going to kind of catch up with Mars. So you can kind of see it catching up with Mars. So here at C, it's catching up with Mars. Notice that C, it's still direct motion. Okay. Now D, it's lined up with Mars, and D, we start to see it, which I don't know D, it goes backwards just a little bit. But what happens? What direction does it go when the Earth overtakes Mars? What direction does it go there? To me, to me, it really definitely goes backwards. It goes backwards. So I'm thinking retrograde motion is kind of the D and the E, kind of here. So F-wise, you can see that here it looks like Mars now. If you compare E to F, I'm thinking Mars looks like it's going direct motion again. Okay, so after it's kind of overtaken Mars, then we have our direct motion. Bottom line, and it might be on the test, might be on one of your questions that you answer, is in order to explain retrograde motion, the backward motion of the planets, that happens when an inner planet overtakes an outer planet. Okay, or an outer planet is overtaken by an inner planet. So anyway, I don't know if I convinced anybody of that, but that's okay. I tried. Go away. You silly. Okay. So we're still with the heliocentric model. You see these planets orbiting the sun counterclockwise, which is correct. And you can kind of see in physics, sometimes we'll do, well, I guess it wouldn't have to even be in physics, but if we give it a certain time frame, can you see where Mercury has traveled the farthest, Venus the second farthest, then Earth and Mars, then Jupiter, then Saturn. Like Saturn's just a little bit shorter than Jupiter, meaning it's just a little bit slower in its orbit. So that's the real deal. We kind of got past a hump there. One of the problems with this figure, and we're going to see that Tycho Brahe, and then actually Kepler made breakthroughs with Tycho Brahe's observations, needed to fix the shape of the orbits. Okay. So this still didn't quite make sense if you make the shape of the planet's orbits circles, basically. So I have a couple of names up here. Tycho Brahe, I kind of liken him to I've seen some pictures of him and his fancy observation tower. No telescopes yet, but he was like nobility that had a lot of time and didn't have TV and that stuff, Netflix. So he went out and observed things. It would be kind of fun, don't you think, back then, if you were to like look at the stars and you would see these planets. The word planet means wanderer. Like over the course of nights or months, you see the planets wander against the background stars. And he watched that movement. And Kepler then was more I don't know if he was poor or not. I think he was kind of bored. But he's very bright. He took Brahe's observations and made actually 3 laws of the planets. So this is just kind of, I think, a precursor to Tycho Brahe. Still didn't quite get it right. He was trying to take the data that he observed, how the planets moved against background stars, and trying to fit a square peg in a round hole, or a round peg in a square hole. Okay. So finally, now this is where I thought we were going to be a minute ago with that parallax. So get back out your parallax idea. Okay, get back out your parallax idea. Well, you told me was that the farther away an object is, the less likely you are to see parallax, right? So one of the things we're going to talk about, a lot of times students like things that blow up. Who doesn't like things that blow up? As long as, it's not your car or something like that. So stars, if they're massive enough, do blow up. They end their lives in an event called a supernova. SN stands for supernova. Now, our sun will not go supernova. It's not massive enough. It would need to have, what we say, 8 times its current mass to go supernova. Okay, so we're okay that way. But when a star blows up, as you might imagine, from basically it goes to being a normal star to being something that you can see. I've heard it described you can see during the daytime even. I mean, I've never seen a supernova like that, but anyway. Then over the course of maybe 2 weeks or so, it decays. It gets dimmer and dimmer and dimmer. So supernova 1572, the way this works is SN supernova 1572 is the year. So I went out and I was like, well, what does that thing look like? And let's just take a look. Oh, don't crash on me. Okay. Now, I've not ever seen this, but actually you can imagine after the star blows up and even after it goes, it kind of dies down to not very bright, because it will, I mentioned a couple weeks. The remnant is still there. So we call that's like the guts of the star that blew up. And actually, we're going to talk about new stars can be born in those guts. It's so cool. They can and they are born. But this is actually supernova 1572. That's the year that the guy observed it in, Tycho Brahe observed it in. And that's what it looks like today. So all things like this kind of take on their own characteristics. So I thought that was kind of pretty. Okay. Now, we said, philosophically speaking, that early on, our universe was perfect. And of course, they thought actually the universe was set up like this. We now know it's set up like this. But in being perfect, the heavens don't change. Okay? So if the heavens don't change, and Tycho Brahe observed a big flash, it wasn't just a flash, it was basically something that became bright for a couple of weeks. That article I read, I think it was even years that it stayed bright. Not real bright, but anyway. So if that was the case, it can't be part of heavens. So what Tycho Brahe said was he called it a new star, the supernova. He said it needs to be relatively close by because you can't mess with our heavens. It's relatively close by. Now, I go back to here. If it's relatively close by, then if you close one eye, close the other eye, you're going to see it move. Think of as the Earth spins on its axis, you should also then, you are literally, it's not just one eye or the other, you're literally changing positions left and right. You should see this at different places relative to, I think in this case we've got the moon. The point is he thought that there was a star that blew up that was somewhere between You're the Earth, somewhere between the Earth and the Moon. Okay, this one's going to sit. Okay. So he looked for parallax, which obviously there should be a parallax, and there was no parallax. Okay. So there must be something bigger than there must be something else going on. Actually, if you have a firm foundation in a philosophical belief, like the heavens are perfect, and something comes along to say, well, your heavens just changed, the star came and went, then I guess they have to revisit that to kind of think it through. So Tycho Brahe made the observations of the planets as they moved against background stars, and he could not come up with a fit because he was stuck to, I mentioned circles, he was stuck to the path of the orbit of the planets being circles, and he was stuck to all of the planets going at the same speed. So anyway, but if what we're going to see is that Kepler, so I guess what I'll do is sometimes I do this. I have Copernicus, and then we said Tycho Brahe, and now I'm going to say Kepler. What Kepler did was to go ahead and take the measurements that Tycho Brahe made, and instead of a circle, make the shape an ellipse. And he said instead of everything going to always the same speed, he said, I'm going to say it's going to be variable speed. Okay. So in order to talk about, here, I'll do this way. So instead of a circle, this is a circle, this is an ellipse. Actually, the circle is a special type of ellipse. I'm going to go ahead and put the belly button of the circle, but I call this an oval. I don't know about you, but this oval or this ellipse actually has what we say two foci. So I've got two foci in kind of the elongated ellipse. And I've got one foci in the circle. Circles are types of ellipses. We say this eccentricity has a value of 0, and the more you flatten out an oval, I'll make it really pretty flat, it goes up to, I think, an eccentricity of 1. So this might have an eccentricity value of, I don't know, 0.7. So in math, we kind of talk about how circular something is, 0, and kind of how it gets flattened out. It gets approaching the number 1. Okay. Okay, so the first law, see, I kind of added some slides back. Kepler has 3 laws. His first law, these are planetary laws. Laws of the planets, dun dun dun. His first law is that this one up here, that the planets orbit in the shapes of ellipses. Planets orbit equals ellipses. That's exactly it. If I ask you on a test, I ask you what Kepler's first law of how the planets orbit the sun, you'd say they orbit in the shape of an ellipse. That's it. And I'll go ahead and say that the sun is at one foci. I'll make this one the sun. And this is like an orbit of a planet. This is my sun. Okay. Kepler's second law, in order to understand his second law, if you figure out his first law, you'd be like, if you're looking at this up here, you'd be like, wow, I can see if the planet's here, it's closer to the sun, and the planet's over here, it's farther from the sun. I'm going to add a few terms there. I'm going to put my planet here, close to the sun. I'm going to call that perihelion. Perihelion. I would write these down. I don't know if they'll be on your, if you guys have notebooks or anything, but I don't remember things very well. We played a game this weekend with my kids. I'm like, can I write this down? Because I can't remember this. But I would jot this down somewhere. Perihelion is when the planet is close to the sun, and aphelion is when the planet is farthest from the sun. So I hope you can read that. Perihelion and aphelion. Yeah, pictures or work? Yeah. And his second law says that it says something about equal areas, but I'll condense it. It basically, what I like to think of as second law is that planets move fastest, and it's a gravity thing, when they're close to the sun. So planets move fastest at perihelion, and guess what? Slowest at aphelion. So it goes kind of like this. The equal areas thing goes like this. If you were to go ahead, my finger is a planet, and wherever my finger is, I can draw a line back to the sun. So if I'm going fastest here at perihelion, I'm going. So if I draw for that time segment, I could draw an area where I started to where I ended, and it kind of looks like almost like a piece of pie. Over here, if I go the same time segment, like that, same time segment, where I started, where I ended, go back here, these areas are equal. Why? Because here I'm booking it, but I don't have very far to go to the sun, and here I'm going so slow, but I have a long way to go back to the sun. So actually, it sweeps out equal, we say equal areas in equal time. But to me, the crux of it is that the planet moves fastest at perihelion and slowest at aphelion.
Does time exist outside of Earth?
Time, yes, time. Time is a funky thing. Time is actually, maybe this is what you're thinking of. Time and space are kind of intertwined. So it's like a fabric thing, almost.
It's not really perceived the same.
So time becomes perceived differently when objects are massive or objects are moving near the speed of light. But if we, for instance, were going to go experience time, if we were going to experience time here, like if we had a spaceship to hover, experience time here, it would be the same thing. But time can be affected by massive objects. Time will slow down. Yeah. But otherwise, we kind of think of our solar system in general doesn't have anything, time on the moon ticks more slowly than time on like an atomic clock. So time is a bit of a variable. Not very perceptible, but it does. So. Okay, Kepler's third law, I said he had 3. I know, there's a lot of law. Let me summarize it. His third law, that's what I'm here to do. Actually, we've kind of already talked about his third law. What did I say with regard to how fast it moves? Neptune versus Mercury. Which one moves more quickly? Mercury. Yeah, that was his third law. That basically said a planet's orbital period, that's how long it takes to complete one cycle around the sun, is equal or is proportional to its average distance from the sun. And there's a cube and a square thing. But basically, you say the farther the planet is from the sun, the more slowly it moves. I'll say farther planets move more slowly. So I'll tell it myself. Sometimes I'll be looking at his second and his third law, and I'll be like, I get them so confused. The second law deals with the same planet relative to its position to the sun. The third law deals with different planets. Okay. So Kepler, again, did all that with Tycho Brahe's observations. We talked about the scientific method, and keep in mind the difference between hypothesis and theory. Remember, I think we talked that with some observations, you come up with your best guess, that's your hypothesis. You come up with ways to test your hypothesis, and you keep doing that. And if it passes all the tests and your colleagues agree, it can be elevated to a theory. Okay? And there is a subtle difference between a theory and a natural law. So that's to say, hopefully, if you've taken a few science classes, including this one, if somebody says it's just a theory, you just want to just come out of your shoes and say, oh. If it's a theory, it started out as a baby hypothesis that was ruggedly tested by everybody in the field, and it was elevated to a theory, okay? All right. So Galileo, I'll put Galileo over there for kind of, I put these in order. So, you know, I had Copernicus, Tycho Brahe, Kepler, and Galileo. There was definitely overlap. Galileo Galilei. Okay, so he definitely started the method of scientific reasoning was definitely coming into view when he did it. Now, he did not invent the telescope, okay, but I think telescopes at that time were mostly used for like sailing and that sort of thing. All right, matey. But he used the telescope to look at neat things in the sky. Okay. Telescopes were invented in Holland. So here's one, and actually I fall under the what a misconception is basically we're all kind of thinking that it's one way, but it really isn't. What do they call those? Like an urban legend sort of thing. Okay. So he was condemned by the church, but it wasn't because, wasn't because of this belief. Remember, we were still kind of segmenting from the geocentric model to the heliocentric model. But I don't know. He got in trouble for backing up Copernicus. So what did Galileo do with his telescope that actually added to the geocentric model, the Copernicus model, and he got in trouble for backing up Copernicus? Well, one of the things that the Ptolemy philosophers would say, again, is about our universe being perfect, including objects, the heavens, and in the heavens is the moon. And the moon is not perfect. One of the things we're hopefully going to do Tuesday is to see some of the beautiful imperfections of the moon that Galileo saw with his telescope. We're going to see with our telescope. So basically, instead of being a smooth, homogeneous surface, it's been slammed for a large part of its life. Okay, it's got craters, and so that was one of the things. Another thing that he did was to, and I don't think we'll probably see this Tuesday night, but we might next time we're out, is to see, we've talked about what's called the Milky Way. It's kind of on our maps, it's kind of that fuzzy looking thing. And the Milky Way, to the naked eye, looks like spilled milk. I think that's how it got its name. But actually, the Milky Way is the same name as the galaxy that our star is in, the Milky Way galaxy. So we're kind of looking into the frisbee of the galaxy. When Galileo looked, he saw, like with his telescope, he saw all these little tiny stars.
Do stars orbit anything?
Yes, stars are moving too. Our sun is moving. And we're moving around, like if this is our galaxy, okay, the center of our galaxy is a supermassive black hole. So the stars need to be moving. I don't know if they're moving counterclockwise or counterclockwise.
So do galaxies.
And then galaxies are moving too. Yeah. Yep.
So at the center of every galaxy, is it a supermassive black hole?
They used to not think so, but now they're really kind of thinking the center of most galaxies is a supermassive black hole.
So those be going around.
What's that?
So we're all just waiting to get sucked in.
No. The way black holes work is if you are in a stable orbit, basically think of it that way. There's no way, unless you get nudged, that you're gonna fall into a black hole. You're just gonna stay in your orbit.
All it takes is a nudge, though.
Well, yeah. And black holes have that thing called an event horizon. If you fall into the event horizon, you're basically going to fall into the black hole. There's no escape.
So do we all go around a supermassive black hole at the center of the Milky Way?
So all the stars orbit the supermassive black hole, and then the galaxies kind of do a dance. Some galaxies are merging, like Milky Way Galaxy and Andromeda Galaxy, both supermassive black holes in the center are coming together.
Yeah, that's right.
Yeah, but most galaxies are kind of getting farther and farther apart from each other. But some of those are doing dance.
Yeah, I forgot ours is like. I wish you could see that. Someday we'll go look in the sky and you'll see another.
Yeah, someday you'll look in the sky and you'll see another galaxy coming in. Yeah, we'll see if we can look at Andromeda Galaxy tomorrow night. So let's pick up here. We'll take a running start on this on Wednesday. Okay? And I'll go ahead and give you guys my phone number in case you're looking for me. So write this down. 319. This is my cell. 750-5991. And I'll probably give it to you later too, because like if you're looking for me, I'll have my phone on, and if you're headed out to the observatory or something, I'll have my phone on, and just it's a good idea. You hit a deer, don't hit any deer. I'll have my phone on. I've never had to hit a deer, so drive carefully out.
I don't know how to work my phone.
You take a picture of it.
Yeah, I'm just gonna do that.
Kids. If you want to wire money, that's fine. Not that much.
So that name told me. Do you know where that comes from?
Only it's like Polish? I don't know. You mean like?
I think like. So what I'm thinking, well, I don't know exactly, but I know that it's spelled the same way, like Ptolemaic, which is like a dynasty in like Egypt.
Okay.
It was like
Whoa.
when like the Greeks and Egyptians like merged cultures.
You should look that up if there's a connection.
It might be. It might be like them because like they have that, you know, the Alexandria and stuff.
Yeah.
So like maybe that's how, you know, astronomy.
I'm liking that. Yeah. Alexandria. That was because I've heard that associated with astronomy.
Yeah. They have that great lighthouse, the Great Lighthouse of Alexandria.
Road trip.
Yeah, yeah. But yeah, that just caught my eye because I'm actually in the art history class and we'll get to the Ptolemaic stuff, and that's where like, you know, Cleopatra and all that, and later Egypt. Sweet. Yeah.
Love it.
I like how it all ties together.
Me too.
I have a question for you.
Yeah.
Yeah, I tried sending the keys last night, but I think I sent them myself.
No, I got something about Mind Tap. Were you able to get in?
Okay, so I thought it was due at 12, so that's my fault on that. But I tried to get in like next week. This week. Yeah, I guess I can't even.
Hey, that should be version chapter 4. Let me pull mine up.
Let me see if I can get this one.
I wonder because if you need a little bit more time, I can do that.
I mean, I can get them done tonight. I don't work today.
What's that?
I don't work today, so I can get them done tonight.
Okay. Let me pull mine up.
But I actually don't really. If I can get it to load, I'll show you what I'm talking about.
Okay, I'm trying to load mine because something didn't quite look right there.
I actually took a video of this last night. I forgot.
Well, this says that they're open till the 15th.
See, because this is what was happening to me last night. Like, I'll try to click on it. And it just. I don't know what it was doing. But this is what it was doing for all of them.
Okay, so if you click on it, there should be a. Because you're used to clicking on that and it letting you in, and it didn't.
And And actually it's up, so what do I have to click on to get it to load? Here, I'll have it up. Because this is for next week. 'Cause- oh my gosh, it's right here.
Let's see. No, it's still very blank.
Oh my gosh. This is not it.
Did you put in the, did you purchase the thing?
Yes, you said.
Yeah, that's,
Let me see if I can.
Let's see if I can go back here and see anything.
Yeah, because it's doing it on this other one too.
Well, it might be that. I'm gonna see if I can. No, I don't see anything that that looks like you're kicked out or anything.
I guess that's probably. I don't know. It says on
But
the
it says
ones that were
access to
due-
none.
The ones that were due last night, there's no little drop arrow thing. I don't know if it's because they were supposed to be in at 11.
let me see if I can,
Extend those. Let's see. So that was chapter 3, right?
Yes.
I'll start with review questions. Let's see if we can edit. I'll change it to when. I'll change it to the 11th.
Was it chapter 3 or 4 you last night?
3 was due last night, so you should be able to get into chapter.
Was 4 due last night?
No.
Because on here it says.
Yeah, I moved it on. I moved it in Canvas though. Yeah.
Let's try to refresh it.
Yeah. So maybe my 4s are locked out. I will. I might need to fix that. I'll do that too now. Because I changed it in Canvas, but I didn't change it in
Yeah, because.
Mind Tab. So hold that
chapter-
thought.
Yeah, all the chapter 4 stuff says it was due last night too.
Okay, I'm changing it now to the 15th. So maybe that's why. So yeah, the 4. So I changed that one. I think I have it at 3, I think. I'll change this one. But you should be able to get in
Or refresh it.
3. Yeah, those needed to be fixed. I'll go back to 3 and make them do Wednesday.
It has their review questions. It's due Wednesday, just not the other activities.
Okay, so can you get into the review questions now?
It's
It is loading?
we'll see.
I hope so. That's good.
Their review question. It's saying I do not have access to Mind Tab. Please contact technical support.
Yeah. And is it a phone number?
it's just a leak. But it's not taking me anywhere. It's giving me a code to report though.
But it was working okay, wasn't it?
Yeah, like the first time I got on and did it worked just fine.
Did you get one from the bookstore or did you buy it through
I
them?
went to the bookstore. Came with this thing.
Mm-hmm.
I think I still have it somewhere.
Trying to see.
I was just trying to do it last
I've
time I
got-
couldn't.
Trying to see if there's someone I can contact.
Got a phone number I could call.
Okay.
You have a class right now.
Nope. Not till noon.
How do you record these from? If you know the extension you want, press pound. Now, if you have your case ID number, just say it or enter it. Or you can say, I don't have one.
RC8344C30.
Got it. Let me look that up real quick. I'm not finding it. But let me make sure I have the right case ID number. I've got 48344630.
That's not what you
Is
said.
that right?
No.
Sorry about that. So please enter it again.
R-C8344C30.
Try again. Sorry, let's use the keypad. If you have your 8-digit case ID number, please enter it now. If you don't have one, press pound.
C8344C30.
No problem. You can say check report, product questions, order status, purchasing,